Welcome back. In example 2, we're asked to explain why this piecewise defined function is discontinuous at x equals 0. So we're already told that it's discontinuous. We just need to explain why it's discontinuous. In other words, we need to explain what it is that's breaking about the definition of continuity, this limit definition that we learned. So why is the limit as x approaches 0 of f of x somehow not equal to f of 0? And there are three possibilities. Well, one of them is that the limit just doesn't exist. Another one is that the function is undefined at x equals 0. And a third is that they just are not equal to each other. So let's explore this and figure out what's going on. Now this is a piecewise defined function, so we have a different formula for the first piece and the second piece. And so the problem, we might suspect, the problem is happening with the limit. Something is probably going wrong with the limit. So let's dive in and try to figure out if that's the case. So let's try to figure out what the limit as x approaches 0 of this function is. Now to do that, we're going to have to approach it from the left and the right sides, because it's the formula, sorry, the formula is different coming in from the left and from the right of x equals 0. Like when we take the limit as x approaches 0 from the left of our function, the y values of the function are calculated by 2 to the x minus 1. So f of x is 2 to the x minus 1 when you're looking at x values that are smaller than 0, that are to the left of 0. So as x approaches 0 from the left, we're going to be using the 2 to the x minus 1. Now to evaluate this limit, we can actually just plug in the x value that we're approaching. So we have 2 to the 0 minus 1, which is 2 to the negative 1. And how can we write that? 1/2. 1/2. That negative 1 exponent brings the 2 down to the bottom of a fraction. Let's take the limit as x approaches 0 from the right. Now we're writing on that second piece because x is positive. It's bigger than 0. So f of x is 3 minus x for this limit. So then when we plug in x equals 0, that x value that we're approaching, we'll have 3 minus 0, which is 3. And there you can see the problem. The left and the right hand limits are not the same, and therefore the regular limit is not going to exist. It does not exist. Let's write that up. Since the left hand limit and the right hand limit are not equal to each other, the regular limit does not exist. So then we can finish off by saying, so this is why f of x is discontinuous at x equals 0. That's kind of proofish. I'm going to put a little box. All right. So the key to everything in this packet is this definition of continuity. The limit is equal to the function value. If you can get that concept in your head, then that's what drives all of these problems in packet 3. Let's go on down to example 3. It says, how would you define f of 2 in a way that makes f of x equals x squared minus 5x plus 6 over x minus 2, so this rational function, continuous at x equals 2? This is called removing the discontinuity that's happening at x equals 2. Now you can tell right away why this function f is discontinuous at x equals 2. Why is that? How can you just tell by looking at it? Yeah, because if you plug in 2, the bottom becomes 0, and that makes the function undefined. So definitely it's going to be discontinuous at x equals 2. But what we're going to do is define f of 2. So we're going to say f of x is like this function everywhere, except at x equals 2, where it's undefined. We're actually going to define the function in a way that makes it continuous. Well, if it's going to be continuous, it's got to satisfy that definition of continuity. So we need the limit as x approaches 2 of our function to equal f of 2. Like, that's the thing. If we're going to define f of 2 in a way that makes the function continuous at x equals 2, well, what does it mean to be continuous at x equals 2? This is what it means to be continuous at x equals 2. The limit as x approaches 2 of f of x is equal to f of 2. That's the definition. So that's driving our whole thought process. Now, we need to figure out what f of 2 is. How would you define f of 2 is what we're looking for. So we're trying to figure out what would f of 2 have to equal. Well, just by what we wrote, f of 2 would have to equal the limit as x approaches 2 of f of x. So let's figure out what that is, and then we'll be able to know what f of 2 is going to have to be. So we'll take the limit as x approaches 2 of f of x. And this turns into an algebraic type of limit. We have to do a little bit of algebra to figure out what this limit is. Now, thinking back to our skills from the previous packet 2, we can plug into, for rational functions, we can plug in the x value we're approaching and see what we get. If the bottom is not 0, then we're done. All we have to do is just plug in that x value. If the bottom is 0 like it is, though, we might have to do some more analysis, or we will have to do some more analysis. Now, when we plug in 2 into the top, we get 2 squared, which is 4, minus 5 times 2, that's 10. So that's negative 6 plus 6 is 0. So we get 0 on the top and 0 on the bottom. And this 0 over 0 type of limit was what we called indeterminate. And our strategy, or one of the strategies that we learned, was to factor the top. Actually, I think this was the only one that we learned for 0 over 0 cases. I guess we did multiply by the conjugate when we had a radical. But that one, technically, we also saw we could factor it as well. So we did learn a couple of techniques. So one of them, though, is factoring. So we're going to factor the top. And because the top is 0 at x equals 2, that gives us a clue that there's going to be a corresponding x minus 2 factor. So that can help you when you're factoring. It's like a kind of like a cheat in a way in terms of factoring, because you know that when you just plugged in 2, the top was 0. So zeros correspond with factors, and so you know x minus 2 has to be a factor. And now inside the limit, we can cancel off this factor of x minus 2. And we're left with x minus 3. That's just a polynomial. So now we can just plug in the x value that we're approaching, and we get negative 1 overall for this limit. So how are we going to define f of 2? We're going to let f of 2 equal that limit, which we just found to be negative 1. What we've done is filled in the hole that was created by this multiplying top and bottom of x minus 3 by x minus 2. Like, basically, this function right here is a line at x minus 3. It's like the same thing as the line x minus 3. The only difference is that there's a hole punched out of it at x equals 2. So all we did by defining f of 2 equals negative 1 is fill in the hole. So visually speaking, it's looking something like this. There was a hole, and now we just filled it in, and now it's continuous all the way through. Now that new function we could call g of x might look like this, a piecewise defined function where the g of x function is just like f of x everywhere except for 2, and at 2 we're going to define our function to be negative 1. So this is a way you could write up the g of x function with the hole filled in. So this new function would be continuous everywhere. Where by everywhere we mean negative infinity to infinity. That's what we mean by everywhere. All right. Let's move on to properties of continuous functions. So these ones are pretty straightforward. They're kind of like the limit properties. So if you have f and g are continuous at x equals c, then all of these functions down below will be continuous at x equals c as well. Like f plus g, if you add the two functions, which what you're doing there is adding the y values of the function. But if you do that, that f plus g, that new function that you get, is going to be continuous at x equals c, as long as f and g are both continuous at x equals c. And if you subtract the functions, or if you multiply them by a constant, or if you multiply the two functions together, or if you divide the two functions together, or if you take a function, raise it to the nth power, or if you take the nth root of the function, all of these will be continuous at x equals c. The only side note that I'd say is that if g is 0 at x equals c, so if g of c is equal to 0, well, then you might lose your continuity. So here you'd have to make sure that g of c is not equal to 0. But that aside, we'll have continuity. Here's a quick explanation for just the f plus g case. The other ones are very similarly described. Basically, you need to show that the limit of the f plus g function as x approaches c is equal to the value of the f plus g function at x equals c. This is the definition of what it means for a function to be continuous at an x value. So we need the limit to equal the function value. So how do we get there? Well, we can use the limit laws that we learned from the previous packet. The limit distributes across addition. So actually the first step we're taking is we're rewriting f as f of x. Just notationally, this introduces the input into it. And then we can distribute the limit across the addition using one of the limit laws. And then the limit as x approaches c of f of x is equal to f of c, because we assumed that f is continuous at x equals c. And then the limit as x approaches c of g of x is equal to g of c, because we assumed that g is continuous at x equals c. But this is, just by definition, f of g plus c. This is what it is. We're not really factoring out a c here. It's just like, by definition, f plus g, that function, is just the y values of f plus the y values of g, which is what's represented here. F of c is the y value of f, and then g of c is the y value of g. So this is just definitional, or notational, you could say. A few other notes. Note that any polynomial p of x would be continuous, because we already mentioned in the previous packet that the limit as x approaches c of p of x is equal to p of c. We stated that after talking about the limit laws and showing how by the limit laws the limit works its way into the x and to the constant term, and you end up just essentially plugging in the x value that you're approaching. So f of x equals x squared plus 3x minus 4 is continuous everywhere. In other words, negative infinity to infinity. So it's continuous everywhere because it's a polynomial. Any rational function p of x over q of x is going to be continuous everywhere except where q of x is not is equal to 0. So it's going to be continuous wherever q of x is not equal to 0. So like f of x equals x plus 1 over x minus 2 would be an example of a rational function. It's going to be continuous everywhere except where the bottom is 0. So except x equals 2. Here are a few functions that are good to have handy. Absolute value of x and sine x and cosine x. These are examples of functions that are continuous everywhere. So you could say for all x, for all real values of x, or you could say negative infinity to infinity, or just everywhere. What about the square root of x? Where would that be continuous? Yeah, that would only be continuous for x values that are greater than or equal to 0. It's undefined for x equals -1, at least when we're talking about real valued functions. Going into complex numbers, that's a whole other realm, but we're keeping it real here. So the square root of x is continuous for all x greater than or equal to 0. If you think about the graph, you can draw it without picking up your pencil. It's continuous for x greater than or equal to 0. It's continuous where it's defined. So this last point here is talking about composing two continuous functions. So if you have f is continuous at a given value c, a given x value of c, and g is continuous at f of c, then when you plug f into g, which looks like this, g compose f, that function will be continuous at x equals c. Because you'll be able to make it through the gauntlet. You'll have f of c is going to be continuous, and then if you look at that f of c right here, and you know that g is continuous there, well then g of f of c is going to be some point on the graph, and because of the continuity, the limit is going to be equal to the value of the function there. So the limit will be equal to g of f of c, and therefore g compose f will be continuous at x equals c. So here's an example. Here the square root of x plus 1 is continuous everywhere in its domain, because if you look at the inner function, the x plus 1, and call that f of x, that's continuous everywhere. And g of x, which would be then the outer function, which is represented as the square root of x, is going to be continuous everywhere on its domain, which would be x greater than or equal to 0. So then if you compose these two, g compose f of x, which means g of f of x, this square root of x plus 1 will be continuous everywhere in its domain. So the composition of two continuous functions will be continuous on its domain. So for example 4, we're asked at what points is the function y equals x plus 3 over x squared minus 3x minus 10 continuous? And here this is a rational function, so we're just going to look at where is the bottom not equal to 0, and that's where it's going to be continuous. Or alternatively, we can think, all right, well, where's that bottom equal to 0? Because those are the problem x values. We have to take those out of where it's continuous. Let's do it that way. We'll say, where is the bottom 0? This is the important part that we need to figure out. Where is that bottom 0? So to figure that out, we're going to factor x squared minus 3x minus 10, and we'll get a positive here and negative here. So x equals negative 2 and x equals 5. These are the two places where the bottom is 0, and therefore the function is undefined, and therefore discontinuous. So where is the function continuous? Well, it's going to be for all x except negative 2 and 5. You could write it up in interval notation if you want as well, like negative infinity to negative 2, and then negative 2 to 5, and then 5 to infinity. We can also just write it out in words here. So connecting what we had here, rational functions are continuous everywhere that the bottom of the fraction is not equal to 0. So that's going to be everywhere except for negative 2 and 5. In example 5, we're asked at what points is the function y equals secant 2x continuous. By the way, for the points here, what I intended to write is x values. So at what x values? We're not looking for points on the graph that is continuous. Otherwise, you'd have to list a whole bunch of these different points. So this is also meaning just x values. So at what x values is the function y equals secant 2x continuous? It might help to rewrite secant 2x as cosine 1 over cosine 2x, right? Secant is like 1 over cosine. And the reason that this helps is because, well, this is going to be defined everywhere except where the bottom is equal to 0. That's going to indicate where our secant graph has those asymptotes and is not defined. So it just helps to write it in this form, 1 over cosine 2x, because then you can see, oh, well, this is going to be undefined where cosine 2x is equal to 0. And that's something that we can figure out, we can grapple with. So we'll take that off to the right. We're going to say where is cosine 2x equal to 0? I was about to say, where are my polynomial chips? Where is cosine 2x equal to 0? Well, if we think about the unit circle, cosine is equal to 0. This is going to be a picture of what 2x would have to be in order for cosine to equal 0. Cosine, I'll write this in red. Cosine is 0 when the x value on the unit circle is 0. Not this x value, but the x value on the unit circle. So that's going to happen right here and right here. So at pi over 2 and 3 pi over 2. Pi over 2 and 3 pi over 2. So when 2x is equal to pi over 2 plus a multiple of 2 pi, we have solutions to this, to this cosine 2x equals 0. And then if 2x is equal to 3 pi over 2 plus a multiple of 2 pi, then we also have solutions. Remember, though, that from precalculus or trigonometry, you can compress both of these sets of solutions into a single expression, pi over 2 plus pi k. That's going to handle all of the coterminal angles at pi over 2 and all the coterminal angles at 3 pi over 2, all in one expression. So you have to reach back and use your trig equation solving skills here. And so that's what 2x would have to equal in order to solve the equation. So what does x have to equal? Well, just divide both sides by 2. And we get x equals pi over 4 plus pi over 2k. So these are the problem x values. At these x values, cosine 2x is equal to 0, which makes the bottom of the fraction 0, and that makes the function undefined. So those are going to be the places where the graph is not continuous, where it's discontinuous. So where is it going to be continuous? Well, everywhere else, for all x except x equals pi over 4, or we don't have to write x equals. We can just write for all except pi over 4 plus 2 pi k. And I'll just write as a reminder what k is. K is just any integer. It's understood at this point, so you don't have to write it, but it's nice to write it and show that you understand what k is. K is any integer. 0, 1, 2, 3, 4, 5, including the negatives, -1, -2, -3. That handles all the coterminal angles. Before we leave continuous functions, I want to mention one useful fact about continuous functions, which is that they satisfy the intermediate value property. A function has this property if it takes on all values between any two function values. So there's a picture over here that shows the graph of a function from x equals a to x equals b, and the y values at x equals a and x equals b are indicated. There's f of a and f of b. And if a function is satisfying this intermediate value property, it means that when you draw the function from x equals a to x equals b, those points there, that all the y values between f of a and f of b are attained. So between f of a and f of b, so between these two function values, all the y values are attained. So if you look at that interval from a to b, and you think about all the graph of the function, then there are going to be y values for that from the points of that graph that go between f of a and f of b. So what the intermediate value theorem says is it ties this with continuous functions. So it says if f is a continuous function on a closed interval a to b, and why not why not, so y sub 0 is any value between f of a and f of b. So in our picture, here's y naught is just some y value between f of a and f of b. Then y naught is equal to f of c for some c in a to b, in the interval from a to b. So in other words, there has to be some point on the graph that has an x value in this interval from a to b. So this is true for each y value between f of a and f of b. So if we pick any y value between f of a and f of b, we'll just call it y naught. And that y value is going to have some corresponding x value. There's going to be some point on the graph that has that y value, in other words. And the x value is going to have to be between a and b. So this is another way of saying that the graph is going to attain all of the y values from f of a to f of b. And this is going to be true if the graph is continuous. I mean, it kind of makes sense. Like if you think about the graph as being the elevation of an airplane. So here it's the elevation of an airplane, and let's say x is this distance that we're traveling, and here the airplane is at some elevation f of a, and the plane is traveling to the right. Well, let's say the plane loses some elevation, it goes down, and then it decides it doesn't want to crash, and then turns around and climbs up to a higher and higher elevation. Eventually it actually passes f of b for a moment, and then it decides it went too high, like Icarus, and then it went back down to f of b. So that's the journey. Well, the main thing is, it didn't really matter exactly what happened in between this x equals a and x equals b, between the start and the end of its journey. The thing is, the plane, if it's going to go from an elevation of f of a to an elevation of f of b, if it's going to go from this point here to this point here, and if the elevation is like a continuous function, which it is, you can't like suddenly teleport up to a higher elevation. You have to go through all the elevations in between to get from one to the next. So in other words, the elevation function is continuous. Well, then we just have to go through all the elevations from f of a to f of b. That's the only way you can get from a lower elevation to a higher elevation. Again, no teleporting allowed. So that's what this intermediate value theorem is saying here. It's saying if f is a continuous function, meaning, on the paper at least, that we have to draw it without picking up our pencil, or you can think of it as being like a plane elevation where you can't like jump, you can't be jumping around or anything, then we have to attain all of the elevations in between. We have to attain all the y values between the starting y value and the ending y value, or the starting elevation and the ending elevation. Let's see how this can help us out with example 6. So example 6 says, use the intermediate value theorem. By the way, this is sometimes abbreviated IVT, because it's kind of a long thing to write out. So use the intermediate value theorem to show that there is a root of the cube root of x equals 1 minus x in the interval from 0 to 1. A root just means a solution to this equation. There's some x value that makes this equation true. It solves this equation. Well, it's weird here because we don't have a function, so it's like, how are we going to use this intermediate value theorem? Well, that's the first thing we're going to do, is we're going to make a function out of this. The way we're going to do that is move all the terms to one side. It actually doesn't matter which side. I'm just going to move them all to the left, but we could have moved all the terms to the right side. And I'm going to call this left side f of x. So this is the first step we're going to take. Let me use this one here. This is like step number 1. So move all the terms to one side of the equation. Call that side that has all the variables f of x. And that's the function that we're going to use for this intermediate value theorem. So then step 2. What we're going to do is say that now the problem turns into, is there an x value that makes the function equal to 0? Right? See, we've just shifted this a little bit from, is there an x value that solves this equation, to, is there an x value that makes the function equal to 0? Well, we're going to show that there has to be some x value between 0 and 1 that makes the function equal to 0. And the way we're going to show that is to show, or to force that, is to find an x value in this interval, and we're going to choose the endpoints here just to keep things simple, that make one function value negative and the other function value positive, so that somewhere in between the function value has to be equal to 0. So here's what I mean. We're going to find f of 0 and f of 1 by just plugging them in. So for f of 0 we get -1. For f of 1 we get, let's see, that's 1 minus 1 plus 1, that's 1. The key thing is that this is a negative number and then this is a positive number. So between these x values, this is kind of like our 0 and our 1 here, and I guess maybe I should just draw it over again. Because the y values both look positive here. One of these y values is negative, one of them is positive. So let me draw a quick little sketch. So here's x equals 0, here's x equals 1, here are the y values of 1 and -1. So what we just did is we just said, all right, f of 0 is equal to -1, f of 1 is equal to +1. So when you're going to connect, if the graph is, if the function's continuous, and it is because we're just adding up and subtracting a bunch of continuous functions, which we know then is going to be continuous. So if this function is continuous, then we're going to have to draw the graph from this point to this point. And somewhere along the line, somewhere between an x value of 0 and an x value of 1, the graph is going to have to cross the x-axis. And at the x-axis, that's where the y value is 0. That's where the function value is equal to 0. So somewhere between 0 and 1, the y value has to equal 0. And then we'll have shown what we want to show. That's what we're looking for, is there an x value on this interval from 0 to 1 that makes the function equal to 0? Yes, there is, and it's somewhere around here. We're not actually going to find the x value, but we're just going to show there has to be an x value. So to finish off the whole exercise, we're going to state that f of x is continuous. This is the third step, by the way. We're going to state that f of x is continuous. So, by the intermediate value theorem, we use the abbreviation IVT, there must be some x in the interval from 0 to 1 such that f of x is equal to 0. This is what the intermediate value theorem would say. There has to be some x value inside the interval from 0 to 1, so that's like our a and our b in this case, such that f of x is equal to 0. That's the y value, that's the y naught that we wanted, was 0. C would represent that x value, but we don't exactly know what c is, so we just don't find it. We don't find that x value that makes the function equal to 0, but it's there somewhere. And that shows then that there has to be some x value that satisfies this equation. That's a root of this equation. So in other words, tying it back to our original question, we've found a root, or we know that there has to be a root, we haven't actually found it, of the equation cube root of x equals 1 minus x. So to recap, what we do is we take the equation that we want to show that there's a root of, move all the terms to one side, and call that side f of x, or however you want to label the function. And then it turns into the problem of, let's show that there has to be some x value that makes the function value equal to 0. And the way we do that is we find some x value in our interval that, or at least or at the edges of our interval, that's negative, another x value that's positive, and in between positive and negatives is 0. So we say that since the function is continuous by IVT, there must be some, so it's not continuous by IVT, it's just that it's continuous and therefore satisfies the condition of IVT. So then by IVT, there must be some x value inside of our interval from 0 to 1, such that the function is equal to 0. That's the only way you can get from a negative to a positive number. From this -1 to a +1, you have to pass 0. And therefore, there's a root of the equation. So these are key parts. When you're showing this proof right here, you do need to write these things out. So you need to take these steps, move all the terms to one side, show that you're finding these function values, one of them that's negative, one of them that's positive. State that f is continuous. That's an important part because that's showing that the intermediate value theorem condition is being satisfied. And then rounding it off by saying what we're asked to show, which is that there has to be some x in the interval such that f of x is equal to 0, and therefore is a root of this equation. So all these key pieces really have to be here to fully do this problem. All right, so that's it for continuous functions, at least for this packet. Thanks so much for watching, and see you around.